Hi, I'm Sam. Thanks for tuning in. I'm recording this video to give you a little demo of a Python project I did called Activation Function Comparison. And as the name suggests, it'll be illustrating the effect activation functions have on a neural network as applied to this very, very basic two-layer neural network that I implemented using NumPy. So no keras or TensorFlow on this, just like I find the math of what's it called? Of neural networks very interesting, so want to apply it. The idea to do this came from this challenge. I forget what website, but it was the objective of the challenge was to create a digit recognizer that would recognize digits from the MNSIT database. And I saw a lot of people trying to do it with math. There's a bunch of YouTube videos on the matter, and I actually made quite a few errors. Well, as did I'm sure, but a few very noticeable errors in how they implemented it. Yeah, and then I also, to make the project a bit more interesting, I decided to mess with the activation functions to see which ones work best. No surprise, it's ReLU. But yeah, I'll do the demonstration first. I made it using tkinter and matplotlib to turn the vector. These are what their handwritten digits look like to the machine, right? They're just 784 columns in a vector of digits ranging from values ranging from 0 to 255, 0 meaning all the way black, 255 meaning all the way white, and then stuff in between varying shades of gray, right? And then tkinter is just it's honestly not even that good of a library, but I knew how to use it, so I used it. Yeah, so we're gonna get desired number of iterations. I just want to test something quick. Whatever. I'll do 200 for brevity. Desired learn rate, hyperparameter temperature. We'll see what that means later on. 0.15. Cool. So running hyperbolic tangent. Oh yeah, and we're specifically comparing hyperbolic tangent, rectified linear unit, and sigmoid as activation functions. But yeah, 200 iterations should be no problem. Just take a quick sec. Almost done. There we go. Okay, so what's the word? So it's in screen. Okay, so we have our, on the x-axis we have our three functions, tanh, ReLU, and sigmoid, and then on the y-axis we have the respective accuracies at a given iteration, and then the sliders whether used to control which iteration. So we have iteration 7 here. You can see 23%, 13%, 24%. Oh, it's compressing weird because of the, there we go. Iterations change. I'm gonna cap out around 85, 86. Yeah, it's to be expected. So ReLU vastly outperformed the other ones. It learned decently faster and also had a higher max, and I find this to be the case even at much higher iterations than, I don't know if you can see this iteration bubble here, but you get the idea. Yeah, at even higher iterations like 1000, 5000, these two seem to cap out at like 94 and 96-ish. Yeah, which I'm is pretty good, at least by my standards. I'm happy with that, especially something just made from math, which we'll get into in just a sec. But first I want to show you the second function of this little UI is so we can enter an image from 1 to 200 to view. What that means is, so we iterated over 200 images, so it's, we can display, let's say the third image, looks like a 4 to me, and then see what they guess. So tanh predicts 7, 8, sigmoid predicts 0. If we go closer to the end, 199, looks like a 3 to me. We get tanh predicts 3, ReLU predicts 3, sigmoid predicts 2. Take in some L's there. Go 198. Looks like an 8, 888, 197, 777. So yeah, that as we get higher, the accuracy gets pretty decent, besides sigmoid for whatever reason. But yeah, fun stuff. Now let's get to the actual code. I'll use this one as my example. Okay, so we set up our activation function. Tanh derivative of tanh is secant squared, hyperbolic secant squared, which is the same as 1 over hyperbolic tangent squared. Then we have softmax, which value raised to exponent over the sum of the values. So then we get nice values that sum to 1 and also fall in between 0 and 1. Getting our predictions is take our final layer, and we have all those values that we just softmax are between 0 and 1 and sum to 1. We take the highest of the values and make that our prediction. Create prediction, kind of same deal. Get current image, blah, blah, construct parameters. Yeah, so obviously we start off with random weights and biases because we don't know what they should be, and then for propagation. So we have our input layer, which is A0 or X or whatever you want to say. And then we have our Z. Z, or layer 1, is equal to our weight 1 dot product with A0 plus bias 1. And then to activate layer 1, we just apply our activation function, of course. That delinearizes it. Fun math stuff. Makes the magic happen. Layer 2, same deal as layer 1. And then to activate Z2, we just take the softmax of layer 2, and then we get those nice values falling between 0 and 1 that sum to 1. And then we encode it, taking the max and target size. Yeah, and return encoded target. Cool. And then backwards propagation is we take the target we just encoded, and then we compare it with our, what's the word? Activate layer 2, which is our final layer. And so the encoded target would be like a form, if there were 3 digits, for example, that they could be like 0, 1, 0. And so that says it's like the digit 1. But our results will not be exactly like 0, 1. Or the ideal case would be they're like 0, 1, 0. But they could be like 0 0.2, 0 0.8, 0 0.1, 0 0.8, 0 0.1. And those all add to 1 between 0 and 1, right? And we want to eliminate that error. We want the we want that second digit to be just completely 1. And the way we measured that is we can find the specific amount of error that each weight and bias, that each weight and bias contributed to the error compared to the target. So we do backwards propagation, take the derivative, which in this case kind of just means the change we want to apply. Then we use those changes we find to update their parameters, and we multiply the change by a hyperparameter, which was our learn rate. We put in 0.15 before. What's the word? Parameter, yeah, and this is how the learn rate affects the learning rate, because if this was number like a 1, then the entirety of the amount we previously decided we would change would be changed. And so it increases the variability between each iteration, each guess. So we implement all of these functions in our gradient descent, blah, 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 blah. Yeah, fun stuff. And I won't go over this in particular because it's honestly kind of boring. It's just launching Balancer window objects and making them do certain things. Yeah, and use matplotlib for like half a second to load the photos. But yeah, that's it. Thanks for watching.